Today in this video, we're going to be talking about dampened trigonometric graphs. What a dampened trigonometric graph is. Later on, I'll be explaining why we're looking at this little bouncing ball GIF thing here, and how we get this funny looking graph that we're looking at right here. Of course, we've been talking about trigonometric wave functions is what we've been doing, and we've already seen this before. Here's the general sine wave equation. And of course we got the formula for getting the period from the frequency and getting the b, the number that sits right here when we know what the period is. And went through that calculation already. We've already done this, but I want to remind you about something that we saw when we were looking at this before. So here's that same function right here, and we can go ahead and we can listen to it. And we've discussed before the fact that that's not a real natural tone. It's called a pure tone. It doesn't get the resonating in there like you would with a musical instrument. So it sounds a little bit funny compared to an actual note on a piano. We went through all that already. But there's another thing about this that's not natural. I want you to just think about it. Okay, if I was to be hitting a key on a piano, other than it not sounding as full with all of that resonance, the strange thing here is that it just keeps on going. That's not exactly the way sound works. That's not the way a lot of things work. Once you finish speaking a word, the sound of that word kind of dissipates and goes away. Once you turn the lights off in a room, the light dissipates and goes away. Well, that's more natural. And so even though we've started representing things with trigonometric wave equations, we need to add to this to get a more full picture. And that's what we're going to attempt to start doing today. And the term is a dampened trigonometric function. Now, I'm going to give you an example of one here and try and explain as far as the equations why this works. But first of all, if you don't have a graphing calculator, please pause this right now and go grab your graphing calculator. Okay, make sure that the mode is in radians today, not degrees. If it's in degrees, none of this is going to work and you're not going to know why. Make sure that it's in radians. If you need to take a minute to do that, pause this and do that. Okay, what I'd like you to do is go to your graphing part where you got y is equal to on your graphing calculator. Go ahead and hit that, and I'd like you to put in two equations. Real simple ones, 1/2 x and -1/2 x. And you can use 0.5 and -0.5 if you want. But go ahead and graph those. And you should get something like that right there. And of course, you just got one line with positive slope, one line with negative. This is all very uninteresting at this level. That's kind of an algebra 1 kind of level thing. But now I'm going to have you add something else. I'm going to have you go back to your y is equal and put in a third equation. Leave these two there. Leave these in. Go to your third equation and put in 1/2 x sine 3x. 1/2 x sine 3x. And then go ahead and graph that. You should end up with something approximately like this. Now let me explain what you're seeing here. Now obviously you've got a wave thing going on, but it's really weird because it gets smaller and then it's getting bigger, and that's really strange. Now just so you know, the 3 here was just to get more waves in there. I just increased the frequency of this thing so you'd see more of them. That has really nothing to do with the reason the picture looks funny. It's because of the 1/2 out here. I've got a function multiplying as a factor of this trigonometric function. And when you put a function in front of a trigonometric function, it acts as what's called a dampening factor, a dampened factor. And there's different ways you could probably think of this. Sometimes I've explained it this way, that the plus and minus versions of this, and that's why I had you put these two in first. The plus and minus versions of this constrain, or if you want, it's like it's bouncing off of them. bouncing back and forth off of them. It constrains it, it holds it in between there the whole time. And so that's why I wanted you to see the lines first. Those are the lines. Now, you could delete the lines and this graph would still look exactly the same. It's just I'm trying to show you that the lines are where the red part, the wave one, actually is going back and forth in between. So you were seeing that. But of course it's caused because of this. Now you need more than just a number, a coefficient. You need a variable. It's got to be a function. So I had to have an x there. You can't just put 1/2 in front of it. All that would do is take your regular wave equation and cut the amplitude in half. You have to have it be a function. So a dampened trigonometric function is anytime you have a function. It doesn't have to necessarily make it smaller. It can make it bigger, like in this case here, because I'm just starting at 0. But it's something that is constraining it. You put something in front, it's got to have a variable, it's got to have an x, and it constrains your trigonometric function between those two parts. And if you want to pause, you can put in all kinds of weird, crazy things, and you can get some just insane looking graphs when you mess around with this stuff. Some people enjoy just messing around, others don't. So if you want to pause it and mess around a little bit, be my guest. Let's take a look at this situation. This is the graph of this is, by the way, a geometric series. We've talked about series and sequence, well, excuse me, geometric sequence. This is a geometric sequence. We've covered those before. And geometric sequences are getting smaller and smaller and smaller by a factor that's the same every time. You're multiplying by the same thing every time. Well, in like this case here, we've got, it was at 5, then it's, I'm not positive, around 3. If you want to round it up, you say 3, okay, so it's only 3/5 of what it started out to be. And so maybe that's it. Maybe you're multiplying by 3/5 every time. Well, you can think of this as a damped trigonometric function, but we'd have to have a constraint here. So this is my first question. Would it be a linear constraint? And the answer is no, that really doesn't work out very well. So then your next guess is probably quadratic. And you know what? That's a pretty good guess, actually. It's got kind of that same curvature right here to possibly be quadratic. It doesn't quite match, so it's kind of like down here it is, but then it's kind of in here, it really isn't working out real well. So it's not quadratic. And like I said, this is mimicking a ball bouncing. A ball bouncing is not a linear relationship, not a quadratic relationship. It's actually an exponential relationship. And I've got a question mark here, but I'm telling you that's what it is. If you put an exponential decay curve in here, that one would fit right along there. So that's an exponential decay. So if we're going to take and model, see, like sound waves or light waves, and we want them to dissipate out, they actually, just like a ball bouncing, will dissipate out exponentially. And so our dampening factor has to be some sort of exponential, in this case decay, not growth, but decay, getting smaller. So this is related to that stuff. It could be that you did this with a sine wave, or you could do this with a cosine wave. It really doesn't matter. But if its dampening factor is exponential, you'll have some version of this. Now, the k, that'll just be a number. The c, that's just going to be a number. This omega, that's just going to be a number. Hopefully you recognize e from when we did logarithms. That's your exponential, or excuse me, your natural growth rate, e, that number. And when it decays exponentially like this, we call it a damped harmonic function. So its harmonic is when it just kind of keeps bouncing back and forth. But this one's a damped one. So it's getting smaller at an exponential rate, which is what happens with sound and with light. With light, it's really fast. And these are the equations you would use. The only difference between these two is, if you remember, the sine wave starts out at the center line, at the average or the middle. So this would be an example of a sine wave one. If it was a cosine one, well, cosine starts out at its most, actually like the ball bouncing. If we were to go back to that ball bouncing, if I wanted to model this one, I would use cosine, because cosine, we always start that curve at its most, at the top. it doesn't really matter. You could do a phase shift and move the cosine to be a sine, or move the sine to be a cosine with a phase shift. So either one, vice versa, it doesn't really matter. But they're decreasing exponentially off to infinity. As time goes on to infinity, this thing is going to decrease exponentially. Now you should be writing at least this one for sure down. So maybe pause if you don't have paper and pencil, pause this, get your notes, and then we're going to fill in what some of these things are. So the amplitude, of course, is going to be controlled by this. And you say, well, is it a function? Is there a variable? Yes, the variable is time, which in this case is that t. Again, k is just going to be a number. Negative c, well, that's just a number. But that t right there, that's your variable, that's time. K is referred to as the initial displacement. K is the initial displacement, how far from equilibrium. The easiest way to actually think of this is back with the ball bouncing graph. I'm going to go back to that here. The initial displacement from the ground here would have been 5. So basically it's how far away did you go from, this would be equilibrium down here, even though you don't see the bottom half. Okay, so in this case, the initial displacement would be all the way up to there. Okay, that's the initial one. Of course, it gets smaller after that, so that's why we use the term initial. C is the damping constant. Okay, so it's, again, that's just going to be a number. Think about two kinds of, it's like a tennis ball and a basketball. They bounce differently because they weigh different amounts, they're made out of different kind of stuff, there's maybe different air pressure in them, and so the way that they react then is going to be different. And that's what this has to do, this damping constant would actually have to do with each thing that you're vibrating. Now, whether you're talking about a ball bouncing or voices or noises, light waves, whatever the thing is that's getting smaller exponentially, they're all going to be made up of different stuff. And so that's what this takes into account there. This is a damping constant depending on the thing that you're talking about. On a piano with the 88 keys, every single key would have a different C in its equation because every string is a little bit thicker or a little bit thinner than the next one, and so the structure of it has something to do with it. You'll never have to, I'm not going to have you guys calculating this, by the way. I'll just be telling you what it is. T, of course, is going to be time. As time goes on, the waves or the bouncing, whatever it is you're talking about, gets smaller and smaller. And then there's this other part here. The B, what we're using in there is the angular velocity, which I know it doesn't seem quite right because last time we talked about angular velocities, we were talking about things spinning. Well, we can still talk kind of like that as an allegory here about it spinning, but that is the angular velocity. And when we did the piano assignment, I don't know if you picked up on this, but if you took 1 revolution times the frequency, so it's going all the way around, how frequently is it going around? When you multiply them together, you get what's called the angular velocity, or in this case, will be the period of the cycle. This is, if you think about this, this is also going to be the P. So in the context of this, we use the omega, but it's related to that period of time. So if you remember when we calculated period of time, it involved the 2 pi. So these are kind of all related in their own way. All right, let me give you an example here. Here's a guitar. We all know that when you pick a string on a guitar, yes, you hear a noise, but eventually it fades out. And that's what we're talking about today, dampening our harmonic motion. It's fading out. So let's say we take this guitar string and we pluck it initially at a 1/2 centimeter above its rest position. You just take your thumb and just move it a little bit and pluck it. It's got a frequency of 98 cycles every second, a damping constant of 0.7. That's going to be your C. I told you these will always just be given to you in these situations. Write a trigonometric function that models the motion of the string y. So y is telling us the height of the string from equilibrium as time t moves on. Okay, so let's go through what we got to figure out here. This is the frequency, which 2 pi times the frequency gives you the omega. This is our initial displacement. How much did we move the string when we plucked it initially? So it's usually the most because it's typically getting smaller. So 0.5, and then it'd go smaller and smaller after that. The damping constant is right there, and again, that's based off of each individual string. And so we end up with this equation right here. Okay, so like I said, go back over here. We've got the frequency times 2 pi, so I doubled that. That's the 196 times pi. And I just stuck that in right there. Now to show you that this works, we're going to go back to that program that I've got where we can listen to sounds. So let me pull that up here, and here's that exact same equation right there. You can see, hey, yeah, it looks like it's fading away. It looks like it's kind of getting smaller off until we don't have anything left. Well, there we go. It just sort of fades. That's way more natural than what it was before. Before, just kind of that eternal, endless tone that just really wouldn't go away. So this is a damped harmonic function. If you recall, if you were in class when I did this, I played a little song for you, and you might not have noticed it, but the curves were different. Then I already had put in my dampening constants out in front, those dampening factors. I'd put them out in front already. Notice it's an exponential decay factor. We've got a negative in the exponent, which means it's getting smaller exponentially. Got those exponential decays, one for each of the notes that I was playing when I was doing that, so that it sounded a little bit more natural with the sound just fading off. Let's take a look at just kind of a generic question here. And I tried to word this very similar to the way you'd see it in your book. In your book it says, using a graphing utility, so your calculator, graph the function of a dampening factor of the function. Describe the behavior of the function as x increases without bound. Okay, so what they want you to do, they want you to graph this. They want you to look at the graph and say, hey, what happens when this thing goes on forever to the right? That's what it's talking about when you do this. Again, to graph these, you have to be in radians. If you're in degrees, you're going to get like a flat line, and you're going to like not know what you did wrong. To get a wave motion, you've got to have it in radians. Also, I did play with the window quite a bit on this so you could see it better. You might want to adjust your window with these, but all I did is I put it in, and there's the graph. Kind of a strange thing. It was really flat, and then all of a sudden you got this nice little wave, and then this is what they want you to discuss. The fact that it pretty much just goes to zero as time goes on. It kind of flattens out again. So it's like something got bumped and then really quickly kind of went back to just sitting at rest. So that would be my answer here. It just goes to zero. As a follow-up question, they might ask you something about a specific y value with a specific x value. I'd say you got two ways to really do this on your calculator. One is to go back to your graph, and you can hit the second trace, or excuse me, just hit trace. Just hit trace and then punch in 3.5. And it'll tell you what the y value is when x is 3.5. Or you could take this and you could put this into your equation, but you'd have to, of course, substitute the x right there with 3.5. And notice there's my y value, which matches that y value, so it doesn't really matter which way. This way is kind of nice because by looking at the graph, you kind of get a sense whether you did it correctly or not. You can kind of say, yeah, that's about 3.5 out. Where here, you're just sort of accepting whatever it tells you. Let's look at an application of this. If you think about when you're driving your car and you hit a pothole or just a hole of some sort, and your wheel bounces. Okay, we put in what are called shock absorbers to help absorb the jolting so we don't feel it as much. And that's what this problem here is about. And I want you guys to try this. So I want you to try it and pause it and then move on and we'll go through it a little bit. So a car hits a bump in the road, shock absorber is compressed and then released. So it squished and then goes back out the way it was. And it's damped harmonic motion. Okay, it bounces a little bit, but then quickly goes back to the way it was before you hit the pothole. If a certain absorber is compressed 8 inches, that will be your initial displacement, by the way. and then vibrates with a damped harmonic motion that has a frequency of 2.5 cycles per second, and a damping constant for that particular shock absorber has a value of 3. Write a trigonometric function that models the displacement of the shock absorber, and we're going to let that time equals 0 be the moment that basically got hit initially. So once you pause it and try to write that equation. Okay, now I don't know if you caught this or noticed, but I used the cosine one, so this might look a little different than yours, but not much. I did cosine because, again, cosine starts at its most, not at its average. And this one would have been extended to its most, and then when it goes into the hole, falls in the hole, it would have gotten squished, so it would have gotten smaller from that point out. So that's why I chose cosine. It just makes more sense for the situation here. All right, you should have an 8 here. You should have a -3 here. You should have ended up with an omega of 5 pi. Again, it's 2 pi times the frequency, which in this case, where did we have our frequency here? Oh, here we go. 2.5 cycles per second. That's your frequency. So that's how I came up with that right there. Now, to continue the problem, you're going to use your function, or use this one. You need to use this one if that's not what you ended up with, to determine the amount of time until the amplitude of vibration is 4 inches. In other words, I want to know what time the y value will have a value of 4 inches. Now, guys, you could do this algebraically. You'd put a 4 in here, and then you would have to work to get t by itself. You're going to run into problems because you'd have the equation with 2 variables that are going to be really hard to put together because one's inside of a trigonometric function, one's inside of a transcendental function. And so that's going to be, I'm not sure how you would go about doing that. So here's what I would recommend with this. Go ahead and graph the thing. So here's me graphing it. And you might have to play with your window to get a nice graph. Once you get that though, then you can take a look and you can answer the question. So it's getting close to 4. So I'm going to just kind of round this and say, oh, that's be about 0.06. You can't put in y values. You can put in x values. So with y values, you're just going to have to get as close as you can and then sort of take an educated guess. So pretty close to 0.06 or close to 6/100ths of a second. Now, guys, if you're not sure, think about if you got something, say, like, 500. Well, think about when you go over a pothole with your car. Does it take 500 seconds to get back to the way you were driving before? No, it happens pretty fast. And so you can sort of use some common sense here to think about whether or not you think you did the right thing there. All right, so getting back to these, what if our factor has a trigonometric thing in the factor? Okay, so the thing that's constraining it also goes through cycles. So I have a thing going through a cycle that's being constrained by a thing that's going through a cycle. Well, that makes the dampening periodic itself. And so I'm going to play this one for you. That's the same one right there. So you get that sound that goes through those cycles. The cycles themselves are repeating, but you get this sound that grows to it and then shrinks to it. You could do the same with the idea of light. If you could constrain light waves, you get brighter, and then it would get darker, and then it would get brighter, and then it would get darker. Any of those periodic type things that you have a constraining factor in front of it, a dampened factor. All right. So here are some problems for you to look at, and here's maybe something for you to think about. So if a ball is bouncing, it should be getting smaller exponentially. But of course it's going downstairs. And somehow this is matching exactly the bounce of it. And how would you go about calculating the drop of each step so that the bounce of this ball appears to never be getting smaller, even though it is getting smaller exponentially? Kind of a weird thing to think about. Have a good day.